Hey everybody, welcome to Super Simple. I'm Marc Teer, the founder of Black Spectacles, and today we're very lucky to be able to have Andrew Watkins with us from Ayers St. Grove. And you know, today I think we have a project that really gets to the heart of what we're trying to showcase, as a part of Super Simple, which is how, different technologies are empowering world-class design. So I think you're going to see that in this project in a lot of different ways, sort of both in the design phase, but then all the way as it sort of makes its way into the construction process. And you should know this is this project, the University of Delaware's Interdisciplinary Science and Engineering Lab project won an AIA Technology and Architectural Practice Award. So it's been sort of recognized for the high level of technological excellence that occurred throughout this entire project. So it should be a really good one. I'm excited to get started and to talk with you, Andrew. Before we get started though, if you'd like to register for our next episode of Super Simple, you can go to blackspectacles.com/podcast to register to attend. And today, you guys know that we have design software tutorials taught by world-class architects, just like Andrew, on blackspectacles.com. So make sure you stick around until the end of this episode because we have a special Black Spectacles promo code to share. And today we'll be taking questions using the GoToWebinar question box, as well as on Twitter using the Super Simple Podcast hashtag. So again, that's Super Simple Podcast hashtag. So to go ahead and get started, again, thank you, Andrew, for sharing your work with us.
Sure.
Can you tell us a little bit about sort of an overview about the University of Delaware's ICE Lab, I think as you call it, project?
Sure. So we've worked with University of Delaware for several years now, probably a couple decades, honestly. And Ayers St. Grove is a trusted advisor on campus, and UD challenged us to come up with a way of rethinking the traditional Georgian architecture typology and aesthetic on campus, and how that could morph into the beginning of a new science precinct on campus. So what we did was we were able to take some of the materials and scale and some of a little bit of the details of typical Georgian architecture and start to meld that into a much more modern building, and one that would reflect the new age of science, teaching and pedagogy and research going into the 21st century. So that's what we were tasked with, and we were able to leverage technologies to do so in all of those things to hopefully come up with a product that is a new thing for Tech Delaware and a new way to learn and teach on campus. So here's a beautiful landscape that sort of is nestled in the crook of this this building, and so the building with the part with the green roof you can see towards the left at the back of the image is an instructional and faculty office wing. Mm-hmm. And the part under the green roof is a big commons where students gather and hang out and eat a bagel before heading to classes. And the classes happen in the wing to the right of the image. There's lots of flexible labs and classrooms between the labs, and then there's also sort of breakout spaces where students can step out of the classroom, have a breakout session, and then they cross the bridge, which is on the far side of the image, and come into the research wing. So there's a lot of, thus the term interdisciplinary, lots of crossover between researchers and students. So it's really kind of an inviting way to bring students into the world of actual real-world research with a clean room, a material synthesis lab, characterization labs, and pretty high-end imaging labs with electron microscope. A lot of stuff in this building, but we think it's a pretty holistic way to design for sciences to bring education into the real-world workplace.
Okay, awesome.
So you can jump to the next slide. So here's a site plan. Again, this is just a simple SketchUp diagram, but we thought very illustrative in how it sits on the site, how the landscape pathways all work within it, and the different program components and how they all kind of reveal themselves to the exteriors, just to blend movement of pedestrians around the building and within the building, and it became sort of a crossroads between the residence halls to the south and the rest of campus to the upper left, if you will. And so it's really kind of ideally sited.
And then
So
just to kind of get in the weeds a little bit
Sure.
here, this is a really nice diagram actually. You said it was a SketchUp diagram, but is it sort of a combo, kind of maybe something done in Illustrator over a CAD plan with, looks like maybe you guys, colored some of the entourage and the landscape and then overlaid
Yeah,
that,
exactly.
overlaid the SketchUp
Sure.
model
Yeah,
into that.
just simple CAD site plan.
Yeah.
The building itself is SketchUp,
Mm-hmm.
and the site work started in SketchUp, and then we did a lot of Illustrator work to sort of make it more graphically appealing. We do have
Sure.
the landscape architecture group in-house, so we
Oh.
worked collaboratively with them to design this and to do the graphic work to
Mm-hmm.
convey the intent to the client.
Awesome.
So the building itself is it's almost 200,000 square feet and about $130 million. It's a pretty big building and fairly expensive, but there's a lot going on in it, and it's trying to accomplish a lot. So
Mm-hmm.
that's a little bit about the program and the cost.
Okay. Awesome.
So we'll start to get a little bit into the tech weeds here a little bit.
Yeah.
On the right is a stacking diagram where you can see all of the Revit models that we developed with our engineering team. And there's 13 in all, and all these things sort of crash down onto each other to make a combined model that we delivered as a coordinated model for the construction manager to use, and we freely share these models with contractors and the owner for simply the availability of the thinking that's embedded in the model. Sometimes we can't convey all of that in a 2D drawing, which is currently still the way we have to deliver this building, but they can understand a little better about our pipe routing and the complex routing of ductwork and things like that, and how we get from the basement all the way to mechanical equipment on the roof.
Mm-hmm.
So the text, I'm not going to read it all, but it is important to kind of highlight the blue text there that the university really wanted to hire the highest end team that they could, both from a design and coordination standpoint, and also one that could deliver the most modern building. And we felt that they felt that the best way to do that was use the most modern delivery techniques, which is ultimately building information modeling. This was not an IPD project, but we definitely acted as if it were, simply because the contractors were always sitting at the table when we were designing. They were weighing in with cost and thoughts of constructability, and we felt it was a great way to collaborate and kind of get feedback real time on a lot of things we usually have to deliver a submission for and get pricing back on.
Yeah, I guess one question here. So just to kind of, this is a really interesting diagram. So I'm going to guess sort of at the top here, this is where we have, your architectural sort of skin model, maybe. Is that right?
Right. Yep. There's actually two different ones. Yep.
Okay. And then this guy right here, the second one from the top it looks like it might be some of the MEP systems.
Those are two different laboratory models. So the laboratory infrastructure was different from the mechanical systems, which was the next layer down.
Okay.
So those are the mechanical, electrical, plumbing, all of the MEP nuts and bolts.
Okay.
That's another two models, and then the bottom one obviously is a structural model.
Okay.
And then the final one is the site model, and we'll talk a little bit more about that later. But the site model was a little more robust than the typical just topography and cuts into the landscape.
Okay. So let me think here. So the way you guys were working for this project, so you were saying this is the structural model, right?
Yeah.
So you guys are all. I guess there's probably a couple of layers to this, right? So you guys specifically went out to find structural consultants, MEP consultants, maybe even lab planning. Maybe you guys do that in-house, I'm not entirely sure. But you specifically went out to find people who could work this way and who could produce design models for you. Is that correct? Do I have a good idea of that?
Absolutely right. We Ayers Synchros has the mentality that we want to work with the best engineers, and we really only work with engineers that work in Revit with us, and we find it's the best way that we can collaborate and coordinate, frankly, our designs to deliver what we hope to be the highest quality design that we can, so that at the end of the day, the client's not paying more than they need to. It's
Sure.
not taking longer to build. So yeah, that's our kind of mandate in-house.
And so the way that you guys are doing that, I mean, because it's one thing for them to make a model, but actually getting into the nuts and bolts of how that really works, you probably have something in your agreements with them where they're, instead of providing CAD drawings for coordination, they're providing BIM models up to a certain level of modeled specificity, and then you guys are doing different, you have regular meetings, and somehow you're doing clash detection. Could you talk through how that actually works?
Sure. At the outset, we deliver a BIM execution plan to all of the engineers,
Okay.
and what that does is define when things are modeled and to what level they are modeled. So you have your level 100 models for really early design stuff, level 200 for into schematics, 300s into the design development. But what that means is I want to see anything that's an inch and a half or greater modeled, because when you get out into the field, it's much harder to move those things once they're in place. So if they model down to that certain extent from design development forward, then that gives us much better chance to find errors as a result of interferences, and that's what that little text box says, that we were able to reduce those errors simply by making sure that everybody understood what was expected of them at the beginning. And then starting in DDs and beyond, we would do monthly Navisworks coordination sessions, clash detection sessions, and that was hosted in our office, but everybody would log in via Works and webinars, and that would let us focus on different parts of the building, and we would assign tasks out of those meetings, and at the next meeting everybody had to come back with those things corrected.
Okay. And how are you actually doing the coordination? I mean, you guys you're bringing them in, you're bringing the models into Navisworks, or you're doing some sort of preliminary, clash detection using a Revit model in Revit, or how are you doing it?
Yeah, that was all done in Navisworks. Okay. So export from Revit direct to Navisworks, and then all of the clash detection was done in there. And then we would, before the meeting even started, we would issue the clash detection reports to the consultants, so they could kind of get a sneak preview of what was going to be expected of them during the meeting.
Okay. Okay. Yeah. So then, really, the meetings were talking through those. So that's really important, and I think key that you guys are issuing those reports prior to the meeting, and the meeting is really just serving the purpose of, is there something we need to talk about here, or is it just, I need to move that thing, right?
Yep, there was a lot of that, yeah.
Sure.
You're showing your pipe going right through your duct. Why are you drawing it like that?
Yeah. Okay. Okay. Cool. So someone's asking if you can share maybe the BIM execution plan, and if you can't, I know that there are some good baseline BIM execution plans that we can share that I think a couple of universities have put them together. So I know we can share that.
Sure. Yeah. Ours is loosely modeled after the Penn State BIM execution plan. That's kind of the Cadillac right now. But we kind of go into another level of, we stay away from the AIA LOD document, and we kind of dive into a little more into specifically when a structural element is modeled, and at what stage is all of the vertical and horizontal ductwork modeled, and on and on. So we can certainly share the execution plan with you, Mark, and then you can distribute that maybe with the final result.
Okay, cool. And then Lewis is asking how long was each meeting. I'm going to guess they vary depending on how many changes there were based on the design and based on the subsequent number of clashes, right? So couple meetings, couple hours from time to time, right?
Exactly. Typically in the early stages, there's not a ton to coordinate just because things aren't getting modeled yet, so they're shorter. But the deeper you get into CDs, the longer they'll last. So it could be a couple hours or more, and then people will start to nod off. So you have to come back again.
Okay, cool. So I want to move on here and let you continue sharing
Sure.
some information about the consulting team and how they work together. So these are the folks
Great.
who you mentioned,
Yep.
those world-class consultants and so forth.
Yep.
Right?
So yeah, the Thornton Tomasetti, they're the one of the best sets of structural engineers. Muller Associates we work with here in Baltimore quite a bit. RK&K is national, and they have a great group here in Baltimore that we work with. And then RFD out in California is one of the great lab planning companies in the country. So
Was that their model that we were looking at here, number 2 there?
Yep.
Okay.
That's the second one down. Correct.
Cool.
So that's the group.
Okay, and this is sort of a diagram about how you guys work together?
Yeah, so the green, if you will, is the design workflow, and so those are all of the tools that we would use at the time anyway in doing our work. Now Revit is all, as most of you know, one package, so you don't have separate pieces and parts for Revit. SketchUp we definitely use in addition to Rhino. Civil 3D, our landscape group used to do a lot of the topography and especially utility modeling. LandCAD was another one that we used to do parametric modeling of landscape and to generate schedules out of those. And LandCAD and SiteWorks work in conjunction with each other.
Okay.
But what's great out of that kind of spin those gray circles of analysis, viz, and QA, quality assurance. Analysis is one that is enabled by having a robust model, and so you can do simulations for things like, okay, I have an air intake on the west side of this building, and my exhaust for generator, for instance, is right below it. How are we going to overcome that now that we see that the generator exhaust goes right back into the building? So just things like that CFD modeling allows us to think about a little more closely. Radiance we did for daylight analysis to do daylight reduction capabilities, which we'll take a look at a little bit later. We'll see some fun things that our structural engineer did with analysis using Tekla structure, and then back in the day, Ecotect was great for doing some sustainability studies and also acoustics, but now Ecotect has been gobbled up and is now built right into Revit.
Okay.
So then visualization, we used 3D Max. Showcase is I'll liken it to a 3D gaming platform almost, that you export your Revit models right to Showcase, can change materials on the fly and kind of give a live demo or walkthrough of your buildings. And then QA was all done with DWFs, just kind of do markups internally. It seems like those are starting to kind of go by the wayside, and everybody's sticking with PDFs, but we still use DWFs on occasion. And then the orange and green overlap is that place where construction managers and the design team kind of coordinate and work together. And I alluded to that earlier, where we freely share our models, and they take their own Navisworks snapshots during construction and take it to the next level. And you can see that little window pane in the bottom there that shows kind of the level to which contractors will model things as construction gets rolling. And then the blue bubble is all of the subcontractors packages, things like CAD Duct and Pipe 3D. Those things all let subcontractors model and then gets fed back into new Navisworks, so that all of these systems are overlapping each other, and you can find issues before they're actually constructed and cost extra money to move.
Okay. Very good. So that's kind of how you guys are organized and sort of how you're working together, which I think I understand. So I think we want to talk about this stair as sort of an interesting way, or sort of like a vignette of how you guys realize something really beautiful using a lot of these different tools, right?
Sure. So yeah, absolutely. So upper left, we still do hand sketches. We still use pens and bum wad, and still kind of develop the idea on the drafting table, if you will. But the sooner we can start modeling these things, the sooner we can start working with our engineers to find out, is it possible? And they can do some analysis to find out if it is possible. And a great result of that is in the lower left, we can start to do some quick visualization things to find out if the client is receptive to it. We can study the lighting within these spaces and how sunlight enters it and artificial lighting. And then the middle, on the bottom middle image, starts to show how the steel is lowered into the opening in the structure, and then the final image on the right of the completed project. So all of these things took a lot of different packages and types of software to accomplish. So it's not just we're doing everything in Revit. It took, if you go to the next slide, Mark, we can look a little more at how the structural engineer worked. So on the left is a fabrication drawing from the steel fabricator. You can see all of the nuts and bolts, the rebar that's embedded in the concrete, all of the different pieces of steel that will be ordered and fabricated at offsite. But on the right, Mark, if you click the, I think it's slide 5 of,
Yeah,
there you
this
go.
guy right here.
You can play that little fun animation. So using Tekla Structure, our engineer did a study of what it would mean if a whole bunch of grad students are jumping up and down on the ends of those blue treads there. So that scared the hell out of us when we first saw it, thinking it's going to move so much. But they assured us that it was scaled up by 100 just so you could see any movement at all. But that's the kind of analysis that building information modeling starts to allow.
Yeah, it's funny. This reminds me, I used to work with a structural engineer, and he would do the same thing and amplify the movement by 100. And I used to always say, I used to come by his desk and say, hey, can you make the building wiggle? Which is kind of what this looks like. Although, okay, cool.
So if you go to the next slide, another fun structural engineering animation, you can play that one. So they started to play with tools they have at their disposal to show the thing falling apart as they drop bowling balls on it. So structural engineers do visualization too.
Yeah, and I'm sure we would all agree, only funny in in the not real world.
Of course, yeah. I don't want to see all the treads falling off of the stringer there.
Yeah, cool.
So here, just a couple of the installation photos. The center one shows the engineer standing under it, and yes, indeed, it's staying there. So he was happy about that. Yeah. And then the next one kind of shows the final product of installed lighting under the treads, sunlight coming in the base. Pretty successful little case study there, just involving how much modeling and analysis we were able to do.
Yeah, so going back here maybe, and just thinking about how this thing was built. So if I go back, here is the digital model that that Thornton Tomasetti created on the left. And so, so this model then was sent to the fabricators, and the fabricators probably replicated that model, meaning they made their own model based on it, and then they use that to fabricate and cut all these different pieces. Is that sort of the right idea?
Absolutely. One other piece to that is they used GPS technology with a total station on the job site to locate the embeds exactly, so that this intricate curving one-sided stair would fall in the correct spot exactly.
So like down there, but then also up here, sort of at the top.
So where it hits the curving beam at the top, both ends of that stringer had to hit it in the exact right place.
Huh. Okay. And so when you say GPS located the embeds, and we talked about this a little bit yesterday, but do you mean that they, let me think about this, that they first indicated where those embeds wanted to be, and then brought that geometry back to the fabricator, and then the fabricator kind of used that to kind of adjust the geometry of the stair, or is it the other way around?
It's kind of the other way around. So the coordinates were established in the Revit model with a architectural model and the structural engineers model. Those
Oh,
coordinates were extracted by the fabricators and used to work with the concrete installers
huh,
to properly place them as concrete was going in. So
huh.
way before the stair was even being fabricated, the steel guy was having to work with the concrete guy to locate everything precisely.
What is the, I mean, what is the tolerance on GPS coordinates?
It's pretty nowadays. It's pretty accurate. You can if we could zoom in on the bottom of that stringer a little bit, there's a little bit of tolerance for areas where we can weld, but maybe only by half an inch or so of variation or
Oh, I see.
deviation.
Okay. Okay. So it's not like it's, to an eighth of an inch or anything like that, but
Uh,
plus or
right,
minus an inch,
exactly.
something like that.
Yeah,
Okay.
nothing in the concrete world is
Well, that's
that
what I was
close. But
wondering. Right. That's what I was wondering. GPS sounds, sounds like it might be pretty fancy or pretty precise, I suppose. But
yep,
okay.
yep.
So that makes sense. So then they're using that to locate the embeds, and then they're regarding shop drawings. You guys probably got shop drawings. Every single piece of steel is on its own page or something like that, and that's the kind of shop. You didn't get digital shop drawings or anything like that, meaning a model or anything like that to review, right?
We did get digital models, but unfortunately nowadays we still can't contractually use
Uh-huh.
those to approve. So we also have to request or make sure that we get
Right.
physical or paper shop drawings to review as well.
Right. Okay. And Michael W. made a good comment about this. Sort of incredulously, you build the models and you still have to deliver things in 2D. And yes, as Andrew is saying, um, that still seems to be the case. So,
There will be a day when we don't have to.
yeah, yeah. Okay, cool. So
And
let's make.
frankly, there. Sorry to interrupt, Mark,
Yeah.
but frankly, there's a movement or a lot of architects that are wary of that because they feel like that the deliverable and the art of architecture is in our drawing. So
Mm,
there's some angst about that in the industry, but
sure.
personally, I feel that the art of architecture is the final product,
Right.
not necessarily the drawings that we deliver.
Right. Yeah, I think we're on the same page on that one for sure. So, okay, cool. So I know we have a handful of other vignettes here relating to this project that we want to talk through.
Sure.
Let's talk a little bit about sustainability here.
Yeah, so University of Delaware does not mandate LEED in their buildings simply because they put emphasis on performance and energy savings of the building, not necessarily having to walk in the front door and see a plaque on the wall. So
Mhm.
we did a lot of lighting calculations and daylight studying to understand a couple of things. One of which the image on the right is done with radiance. And that was letting us understand how much light we needed on the exterior at the front entrance to highlight the slate walls, as well as how much light is needed in those front study spaces. And from those radiance studies, the image on the left is directly from Revit, and you can see all of the circuiting is all tied together into so we can immediately go from analysis to documentation. So there's very little manual labor involved in studying light levels and going to documenting the building.
Okay.
So what we were able to do using those tools in concert was that we could demonstrate a much lower use of lighting power density and still achieve the needed foot candles on work surfaces and different spaces.
Okay. And you talked, if I remember correctly, you talked about how you're able to get this information out of the model. Can you talk a little bit about that?
Radiance is a separate package from Revit, although Revit has it all built in now. But there's a export connection between the two,
Mhm.
and once you've pulled it out into radiance, you do different light studies and scenarios, and then you're able to extract that and feed it back into Revit so that your schedules stay updated, your light fixtures and wattages and bulbs all stay updated and correct.
So you're actually able to sound simple, turn the lights up and turn the lights down in order to kind of get the right kind of result and radiance, and then you're able to take those adjustments and send that back into Revit and update all your schedules, right?
Yep, absolutely. You can study fluorescence, incandescence, LEDs, even the color temperature of the bulbs, spacings, and all of that stuff kind of goes into design decision making, as well as making sure that you're following codes for different space types.
I've never actually used Radiance. So then somehow you're able to see, I mean, it's one thing to be able to visualize it, but it's another thing, as you said, to make sure that you're hitting the code required, minimums for the different foot candles and different parts of the floors and so on. So you can see that in Radiance. It somehow maps that onto the floors and desks and so forth.
Exactly. It gives you basically a foot candle map of surfaces that you can just kind of look at and average across the surface or a floor space.
That's awesome. As I say, I've never used Radiance before, so that's pretty impressive. I can imagine a designer getting their hands on this software and realizing what they can do and the way they can tune their building. It would kind of make them go wild.
So there is a phenomenon, Mark, called digital overload that a lot of designers are met with.
Yeah.
The more tools we have to learn, the less efficient we get in all of them. So there's a fine line between doing everything and doing the important big things. So
I know, but can't you imagine a designer seing this and saying, "Wait a minute, I can do what?"
Yeah. Yep.
You come over here, sit down. Let's adjust these colors and let's adjust the let's reduce the fixtures and so forth. You can kind of see how they could go wild in this. It's pretty cool. Okay, good. So that's a little bit about sustainability. You have a nice slide here about fabrication. Let's talk about that too.
Sure. So we've talked about steel quite a bit. I should mention, this is a combination of post-tension concrete and steel building. And so the steel fabricator worked closely with the concrete guy as well as the structural engineer to develop these part models, essentially. And as I mentioned, they would send these to us to confirm that their thinking is correct. And from those models, they were able to extract bills for purchase of the steel parts. And a lot of these were fabricated off-site and craned onto the building. So the image on the right there, you can see the installed progress of the steel frame that kind of hangs over the concrete infrastructure or skeleton of the building. So it's a very connected digital workflow that allows things to happen quickly. A lot of things are shop fabricated nowadays and brought on site, almost like a menu that you can order from, and it all gets delivered and bolted together, and voila, you have a building.
Mm-hmm. And again, so these are their models. These are the subcontractors' models. They used the design team's model, so they used TT's model, presumably.
Yep.
And is that maybe TT's floor as well? So they used probably both of those things, and then they built their own model to their own specifications. And then again, coordinating all this stuff and making sure that everything fit. They go out to the field. Are they still GPS locating all the connection points and so forth?
Yep. All those embeds are coordinated with the concrete installer. The starting point is the structural Revit model. It's taken into whichever package the steel guy is working in. In this case, it's Tekla Steel or Tekla Structure, and they add all of the connection designs, all of the bolting patterns, the gusset plates, on and on, that typically the structural engineers do not model. And that's all kind of sent back to us to confirm that their thinking matches our design intent, including even edge of slab plans for that matter. And it's all kind of overlaid to confirm design to installation procedures, and then they start to fabricate as soon as we're in agreement, and away we go.
So, I mean, the interesting part here that presumably architects have nothing to do with is the idea that, the GC here is working with subcontractors who are capable of producing these kinds of models, because even though it's 2016, presumably not the majority of subcontractors can work like this. So can you talk about how, I mean, I don't know, when was the GC involved in this project, presumably early on, and how is it that that they sort of endeavored to go find folks who could work digitally like this?
Sure. So, as I mentioned, University of Delaware wanted the best team to come together to build this building,
Mm-hmm.
and Whiting Turner was the construction manager that they selected, and they were picked fairly early on in design. So they definitely were coming to project meetings to listen to our design process, kind of get a sense of our methodology, how we were making decisions and why, and that kind of gave them an insight into how we work and the things that were going to be important in the building to everybody, including the client. And as a result, when it came time to establish a GMP and select subcontractors, they made sure that all of these subs were going to be using digital technologies to do their work as well. So they, in the contracts, all mandated that they were going to have BIM services in place so that they could deliver, for instance, their steel or their curtain wall or their building cladding systems in a package that would coordinate in Navisworks.
That's interesting. Okay, so I mean, in many ways, that's kind of where the rubber meets the road. That's how you get something that you're able to talk about like this. Is you have and in your case, you had a construction manager who's sort of quarterbacking the whole thing, and so it's their contracts that they're sending out and the requirements they're putting in those agreements that is resulting in subcontractors who can produce digital models like this.
Correct. Yes.
Okay.
It's a sort of a forced marriage of technologies to ensure an outcome, essentially.
Mm-hmm. Yeah. Okay. Yeah, I don't think. What are the here? You're talking about the prefabricated pieces here. I mean, how much of this is prefabricated? I mean, is it like this entire kind of section here, or what's actually prefabricated here?
Yeah, those whole we call them outriggers. Those whole outrigger sections were all shop fabricated and then
So
welded in place.
This whole sort
Yep.
of section here, and then the one below it, and so forth.
Yep, absolutely. A lot of that stuff was all shop fabbed and then kind of bolted and/or welded in place onto the main structural components.
Okay, and then these guys are sort of infilled the vertical sections here.
Yeah, even a lot of that, the vertical sections were all shop installed, and then a crane just holds it in place while things are welded, and it's all set and on to the next section.
Okay, got it. Let's talk about site information modeling.
Yeah, so this was a little bit of background on Newark, Delaware. It's very close to sea level, so there's a lot of groundwater that's not at all very deep below surface. So you can see our in the image here, our deep foundation system. It's all on micropiles, and there's a lot of existing infrastructure that's serving campus here. So we had a lot of things to work around when putting in new utility infrastructure for our building. So we challenged RK&K, our civil engineer, to use Civil 3D and work with our landscape folks to model not only the existing infrastructure but also all of the proposed, so that we could ensure that it was going to be above sea level, it was above groundwater, and that it was all coordinated so that we weren't digging up trenches that had telecom systems in them, or rerouting sanitary or storm lines, that it all kind of worked together as a new seamless package. And that was really important because This was all being done before any of the excavation was going to start happening for the building, so that it was an early package to do all of the site work. And the lines that were going to come into the building were installed prior to the foundation walls going in place. So a little bit out of sequence, but that's why the extra level of coordination was required. So we were able to optimize the layout simply by doing a little more due diligence in modeling the site work as well.
Yeah, that's what I'm wondering is where did you get all this information from? Because usually it's on some, very inaccurate plan. You call, on a slew of inaccurate plans. So how do you have any idea where all this stuff is?
Yeah, it's a great question. It's a good combination of ground penetrating radar, GPR, and potholing, digging down and actually finding these things and looking at as-builts, which you are absolutely right, they're rarely correct, but all of those things let us get as close as we possibly could to finding the existing utilities so that we could hopefully build in a little bit of tolerance to avoid them as we put new work in.
Okay. So it wasn't like you guys were given some sort of GIS model or something that had all this stuff already in it, but you guys did good old-fashioned, kind of iterating between as-builds and then going out there and, really checking to see what's there in order to make it happen.
Absolutely right. I would love to have a GIS model of existing infrastructure, but not too many entities have those things.
Yeah, definitely. Okay, so let's talk a little bit about maybe move into some of the later stages of this project, and here maybe actually let's take a moment. This is the final result of all that gritty work.
So just to point out that there are some bioswales built into the landscape here to take a lot of the runoff from the building and the roof areas to allow ground to allow stormwater to naturally go back into the ground rather than adding it to an already overburdened storm system. So
is that maybe these sections here? Is that what these are?
Yeah, there's a. I wish I could point to it, but there's a sort of right above your cursor there's an area where there are orange ground cover.
These guys?
And grasses. Yep. And then on the other side of the sidewalk, there's another one. Yep, and then to the north of the sidewalk on the opposite side, there's a large one on that side. So all of those areas were calculated in into the stormwater runoff calcs.
Okay, got it. Let's move into the sort of the actual construction phase of this project. Of course, we led a lot of our marketing around robotic bulldozers. So let's talk through this. Again, we've already talked a lot about GPS, so let's keep that conversation going.
Yes. Perhaps my favorite little story about this job is all of that site modeling that we did with landscape and civil. The models were fed right into total stations, and those total stations, you can see the GPS units right on the blade of the bulldozer there. They were basically guiding the blade and tilting it back and forth, up and down to guide the bulldozer as it moved along robotically. You can actually see the guy in the orange vest on the upper left there. He's the one that's sort of controlling it, but the GPS unit is the one that's tilting the blade to do the micro grading around the site, just to get the grading just right around the building. So it's this thing next level of control.
It's actually, I mean, it's creating the correct elevation there based on GPS coordinates.
Yep. That was all embedded in the site model that we gave the contractors.
And I mean, let me ask a dumb question here. I mean, is this technology somehow inherently more accurate? Is it faster? Is it cheaper? I mean, usually those are the things that kind of, that factor into this.
Yeah, I don't know that it's cheaper,
okay.
But it gives a much greater level of control and accuracy when the typically site work is a little bit of a rough science, we'll call it. It's not necessarily highly accurate, nor so we spend a lot of time working out the grades around the building for ADA purposes and runoff and making sure the water's running away from the building, and a lot of that gets lost in the translation between modeling and documentation and understanding of design intent. So this is kind of removing a lot of the human error out of it, if you will.
Okay. My favorite image of them all. Let's talk about this this section here.
Yeah, so this is just one of the shots of the construction manager's combined models of all of the subcontractors, and you can see how many different systems all have to have interplay with each other, and how much coordination goes into putting a building like this together. Excuse me. So all of these systems are then tied to virtual scheduling software, so that everybody sort of has a good understanding of, okay, this week here's what has to happen in instruction lab 102. The sprinkler guy goes, and the room next door, the duct guy is going in right after the sprinkler guy, and on and on. So it's just a continual check of systems that are going on in the building, simply to avoid those deadly change orders that become so costly to projects.
Okay, so this is sort of almost a final model here, but this really represents probably a ton of back and forth meetings and weekly, I don't even know, daily coordination meetings where maybe the architect and the design team, when they're needed, are sort of involved and sort of looking over the shoulder and commenting when necessary. But for the most part, these guys are, you've already sort of expressed your intent, the design intent, through your models. And so,
right.
And it's not just an architectural model, it's an architectural model, it's a structural model, it's an MEP model, and you've modeled everything down to 1.5 inches. So can you talk about the kinds of things you guys discovered through the actual construction coordination process that maybe you didn't uncover, through the design coordination process? Was there like a certain couple of categories of stuff you found?
Yeah, I mean, apologies to any mechanical engineers that are in the audience, but we find that the M trade is the one that ends up causing a lot of the, we'll call them RFI issues in the field, simply because the things that we design, the equipment that we select to design to, isn't always the one that gets selected in when it comes time to procure equipment. So, we try to be as generic as possible, but maybe the air handler is a different brand, so it's a little bit different footprint. So maybe it comes out a little bit differently, so it doesn't quite line up with the shaft. And then there's a misunderstanding about, is that duct insulated? If so, I have to make the shaft a little bit bigger, and then it has to clear all of these other systems. So that's kind of the big thing that you start to uncover as the specific information about manufacturers and construction tolerances all get layered in there on top of each other. But what it does let us find out is the ceiling might have to drop another inch or two. It doesn't really affect the space that terribly, so yeah, we can live with that. Or no, our sight lines for projection in that classroom are compromised if we lower the ceiling. Let's find another solution.
Okay, that's really interesting. So just the process of buying all the stuff for this building, and wanting to buy the most efficient and the least expensive things for the building may mean that everything doesn't fit. And if it doesn't fit, then everyone's kind of got to put their heads together to figure out how to make it fit. Absolutely,
it's all part of the collaboration of between design team and construction team.
So how does that actual collaboration work? Somebody from from the construction management team, they're sort of the owner of the model, and so they're the ones who are sort of negotiating all the stuff that's in the design models versus all the stuff that's in the the actual subcontractor models.
Yeah, that's exactly right. And once the subcontract models are all compiled and kind of coalesced into one, then the design team is participating in these probably weekly coordination meetings, sometimes every other day, something like that. We have pretty regular site presence on jobs like this, so whether it's an architect or engineer, somebody's always on the job site kind of working with these guys to resolve this stuff before it becomes a serious problem that we have to start removing and reinstalling.
And is it the same thing that you were describing in the design process where the construction manager is bringing all the models together, running clash detection in Navisworks, sending out that report to all the different subcontractors, and then the meeting is basically serves the purpose of, going through the list of all the clashes and, sorting through the, I got to move that thing versus, gee guys, we got a real problem here. We need to kind of talk about how to solve this. Is that kind of the idea?
Yeah, very similar. Yes. The one extra step I would say is that they've sequenced the building in a certain way to make their construction work with all of their lay down areas and crane locations. So they're looking at very specific areas of the building each day or each week in order to solve problems in that area so that they can then install them the next day or that day. So it becomes much more tied to construction sequencing and time.
And I have to say, I don't have a lot of experience with the construction sequencing model that you talked about, but I assume it's probably somewhat similar in that it identifies sort of clashes of time or clashes of space when you're trying to, put a bunch of steel in one area and then have it set somewhere else. If there's a bunch of whatever, rebar in one area, but there's supposed to be a bunch of beams there, it's sort of sorting through those different conflicts of sort of space and time. Did you get any experience sort of seeing the models that they put together for sequencing?
Yeah, I did. And they used Synchro to kind of tie geometry to time. It didn't quite. It's not quite to the level of sophistication that you described. It's more kind of a visual way to understand the next system to go into an area of the building or space. So. Okay.
Did I spell it right?
Yeah, you got it.
Okay, cool. Some other pretty awesome photos here.
Yeah, so these next two are lab systems that were really highly modeled, just so all of the installers could understand each system that had to go into these labs, how it coordinated with lights, the utility carriers for the overhead systems, the ceiling grid, all of the sprinklers, the emergency showers. All of these systems have to kind of tie into each other. So. There's a lot that goes into all of these models.
Yeah, so this is sort of like a digital mock-up, basically, or digital mock-up prototype.
Yeah, it's a dress rehearsal for actual installation.
Okay.
So yeah, I love this one too. So the model on the right, or the image on the right, or excuse me, the left, is the modeled version of the conduit coming into the main electric room. And the one in the middle is the actual installed version of that, and you can see they're dead-on matches to each other. And then the one on the right is information modeled panel board. So all of the circuits that are going to each panel board are kind of embedded in this model, so they can understand that the panel board on the right controls all of the lighting in the east wing, the instructional wing, and on and on.
Okay. And then here we talked a little bit about, or we should talk a little bit about, you said, you described this as virtual sequencing. What does that mean here?
Yeah, so a little bit tied to Synchro. This is more kind of an augmented reality look on an iPad of you're looking at a shaft that's complete, and this guy's looking at his tablet, looking kind of getting a sense of what's the next thing to be installed in this shaft, so he can kind of tilt the tablet up and down and look at the things in context for where they're going to be and making sure that they're still going to fit based on field conditions. So
again, this thing is connected. That this software has GPS located, knows where it is, and knows where the iPad is in space, and subsequently it's mapping that to your GPS located model that the construction manager provided. Is that right?
Yeah, exactly right.
And that's how it knows how to show this person, what's going to be next there. Huh. Awesome. Okay. And then we talked a little bit about prefab for steel. Here's prefab for some of the guts of the building. Can you talk about this?
Yeah, sure. The next series here is kind of just talking about prefab, which we already touched on a little bit, but these models talked about the stainless steel ductwork that are serving the clean room, and a lot of this stuff was being prefabbed based on modeled content that originated with our lab planners.
Mm-hmm.
And all of this stuff was, you can go to the next slide, and it's all being installed off and fabricated off site. And you can see the guy cutting the stainless steel ductwork. It's being lifted into the building by crane, dropped in sight, dropped in place, and then installed accordingly. So, just.
And again, I'm wondering.
Yeah.
I'm wondering here. So this ductwork, presumably, again, it was modeled in the design process, and so it's in the design models, but maybe in the actual fabrication models, it's slightly different. And so you guys, they're going through the coordination to make sure that everything really, really fits, in the construction process. And once they had that assurance, then there must be some sort of sign-off process where, there's a certain, a certain piece or certain sections or certain areas that, the team has sort of agreed, they all fit, or the construction manager agrees that everything fits. Is that true?
Yeah, absolutely right. Again, this all kind of refers back to the Navisworks model and making sure that you can see there's cable tray, there's all the service piping for the clean room, and it's all kind of made sure that all of the interplay is all working together to make sure that so when the crane drops it in place, it's going to work with everything that's already installed or to be installed.
Okay, but there must be some sort of formal, okay, guys, this section, it's all coordinated, everyone has to, sign their name in blood or something like that before everyone goes off and makes their stuff.
Yeah, pretty much, yeah. We all give our normal formal approvals.
Okay, cool. So then moving forward to continue to talk about prefab, let's talk about the metal panels here that we're seeing in tan and silver.
Sure, so that's a building skin system by Centria. It's a metal panel system that's all insulated, and it's on essentially this outrigger or furring system that needs to tie into both steel and concrete structures. So all of the different attachment methods need to be modeled and understood so that the structural people that are installing steel and concrete know where these things need to attach, where embeds need to be included. And then they also, if you go to the next slide, you can see how it was also used as an intent for, the pattern that we designed, how the reveals work, how the different colors all kind of get laid in for different panels.
Mm-hmm. And then the final product.
Yeah, so then there's the final. You can see all the different colors laid on top of each other.
Yeah, which looks a lot nicer than their fabrication model, by the way.
Thanks.
So, okay, cool. And then we talked a little bit, and these next two slides sort of go together. But here we want to talk about the prefabrication or the GPS location of the precast.
Yeah, so the precaster worked with the concrete installer to design the embed locations well prior to the precast panels even being fabricated, and the embeds were located using, again, GPS technology as concrete was being installed, and then the precaster could then come swing their panels in their large precast panels in place, and then it all gets kind of welded in place into those pre-located embed locations.
Okay, so same technology we've talked about a few times, and then here, what are we seeing here?
Yeah, so the panel on the right, the image on the right is a precast panel system with slate embedded into it. We talked about the materials at the beginning of the discussion. You can see the metal tabs at the top of that panel. Those are going to be welded onto the embeds that are already in place in the concrete structure.
Okay, So this is really the thing that they want to line up. And of course, again, the tolerance here is pretty sharp. I mean, you guys probably have to be,
Yep.
pretty tight. There's probably a little bit of play in the connection pieces here, but ultimately they need to be pretty dang close.
Right.
Okay, cool. And this is the final result. This is the this wall here
Yeah, you got it.
is the wall we're looking at, right?
Yep. So that's all slate embedded into a precast concrete panel, and then all kind of swung into place.
Awesome. And guys, as we're getting close to the last slide or two here, if you guys have any questions you want to throw into the GoToWebinar question box or throw them into the Super Simple Podcast hashtag on Twitter, you can do that, and we'll try to grab your questions here toward the end of our session. But I know, Andrew, that you wanted to talk a little bit about the statement from the University of Delaware here.
Yeah, I'll just highlight the orange sentence there, that BIM was the catalyst for continuous improvement that was crucial to the continued success of this important project. So ultimately, the client recognized that the technologies that we used was a driving force behind the success.
Got it. Yeah, I think it's interesting. I feel like a lot of these projects, when they're driven by the client, it's really amazing. And I think you see this a lot with with clients who have a lot of real estate and who are very smart and very knowledgeable about what kind of design team and construction team they want to ultimately hire to create their buildings that they're going to ultimately have for a long time. And it seems like whenever you have that type of a client, there is this opportunity to sort of do things the right way and take advantage of all that a lot of different new digital technologies do allow us to do as architects. So it's I imagine for you guys it's pretty awesome to actually be a part of the entire process from beginning to end, but not only just be a part of it, but to sort of lead it. Is that right?
Yeah, absolutely. We kind of view technology as a tool to let us do our jobs better and to work with all of those connected with the construction process in a way that wasn't possible in the past.
Yeah.
So just this last statement from Delaware, our expectations were exceeded as a result of constant collaboration and communication. So we think we ended up with a pretty great facility for them.
Yeah, that's awesome. And I guess you think, in almost every case when architects are involved, we're doing a one-off building. We're designing the 747 for the first time. So it's got to be pretty rewarding for the design team to have succeeded. And I think you had some stats, right? That a tiny percentage of conflicts or change orders or RFIs resulted from geometric conflicts or things basically not fitting.
Exactly right. Yeah, historical levels are 15% of change orders are a result of geometric clashes, and we got that well down to in the 3 or 4% range. So a pretty dramatic reduction in change orders just as a result of things that we can catch when we're designing a building.
Mm-hmm. Yeah, awesome. All right, well, thank you so much, Andrew, for sharing this project with all of us. It's really inspiring, and I think it's a wonderful example of, again, how technology is enabling not just us as designers to, realize the things that we want to realize, but for the folks who we work for, our clients to see these projects come out the way that we tell them that they're going to come out. So congratulations on some great work, and thanks so much for sharing it with us. And thanks for everyone who asked questions during the session today. If you'd like to attend our next Super Simple podcast, you can go to blackspectacles.com/supersimple, and you can register to attend the next one where you get to share questions and comments along the way, and get to hear another wonderful story about how technology is empowering world-class design. If you're interested in learning more about our software tutorial curriculum, you can go to blackspectacles.com, where you can try out any of the free courses. And for those of you who are ready to start learning some new design tools, you can use coupon code 61516SSYT15. to get a 15% discount for the entire duration of your Black Spectacles software tutorial membership. And finally, please leave a comment below the video to let us know what you think and share any suggestions you may have. I promise we'll read every word that you write and use them to tune our next episodes. So thanks for watching.